Yuck. I meant to call roll before we started recording. So let me pause.
Jim.
Jeremy, got it. Oh, I saw you on here. There you are. Okay. Now, there was a question. Where do you find the Screencast-O-Matic? Well, Screencast-O-Matic uploads to YouTube. So, do you know how to search YouTube? Okay, look for either my name or MTH113 on YouTube. And students have been able to find it that way. Find the most recent of the last recorded. I think that's how it said it, recorded so many days ago. If you do so many months ago, that would be last spring, okay, or possibly even last fall. Okay, so look for the ones that, the most recent. Now, here's my sad song, okay. I think I may have told y'all I was going to carry all my stuff over to the Birmingham campus on Friday because that was my biggest chunk of office hours. I was going to try to get all the blackboards straightened out for all the classes. I didn't think I'd be able to get them all done, but I thought I'd make good progress, and I was going to carry it home on the weekend and hopefully finish them up. Well, I carried everything over on Friday, and before I could start doing the blackboard stuff, though, I had to, because I'm math department chair, I had to cancel the last 3 classes that were low enrolled, and I always like to call the students before I cancel classes. So I got the first class in front of me, called the first student in that class, got that phone call made. Before I could finish the phone call, in came students. And they never stopped, okay? Or instructors or various people that got called there and there, all over the place, and never got to cancel the 3 classes until I was already way late leaving. And before I left, I sat down and canceled the 3 classes without being able to call any more of the students. Made me sick. But I didn't get to do anything in Blackboard at all on Friday. Okay, then over the weekend, we were out of town for part of the time, but when we got back Sunday evening, I started working on it and got some of the things updated. But when I went to upload it on Blackboard, Blackboard was down. And I could not do a thing on Blackboard. So yesterday afternoon, and let me get your name, please. Second?
Tyler Dowdale.
Okay, got it. Sorry. Okay. All right. Anyone else come in? Justin did. Okay. Anyone else come in? Sister called roll. Okay. And so I couldn't update anything at home on Blackboard. I got things corrected. And then yesterday I had 2 hours office hour in the afternoon, and I got started. Okay. And I got all my Math 112. No, I didn't. I get most of that done, but I kept running into issues with the bookstore, issues with instructors, issues with text, issues with all sorts of things. And finally, I took them all home again last night and got finished getting Math 112 done. Started doing 113. Now, I had to leave this computer here because Dr. Bryant uses it for his physics classes on Monday, Wednesday afternoon. So I had to use the old laptop we had at home. And it has that sorry Windows Vista program as an operating system. Worst operating system I think I've ever seen. And it didn't interact well with Blackboard, so everything took twice as long as what it needed to. And then finally, when I got Math 112 done, I started to do 113, and the battery died on the computer. So I had to go plug it in, and I said, I'm tired, I'll give up. So I won't have any office hours today at all, except over lunch. But then I'll take the stuff home again today, and maybe have some time tonight. But my wife already has a honey-do list for me at home, so I don't know if I'm going to get any of it done today, tonight or not. But I'll try. The most likely is next, on Wednesday afternoon, I have 2 hours office hours then. Hopefully I can get stuff done then. Okay. Any question on anything we've done up till now? All right. Radian measure. we talked about this last time. Remember, radian is not really a unit. Degrees are a unit. Radians is just a ratio, but we treat it as if it's a unit. So 1 radian is the measure of the central angle theta that intercepts an arc S equal to the length of that radius of the circle. Okay? Now, figure 4.5 was that? Yeah, here we go. If this is your radius and that the arc length, then that theta is exactly 1 radian. Now, are all things 1 radian? No. So for any angle here, then the angle measure is the ratio of the arc length to the radius. And that's what this formula tells you. Your theta, the measure of theta measured in radians, even though it's not really a unit, is the ratio of the subtended arc to the radius or that forms that arc. And let me get your name, please. Doc, okay. Got it. All right. Anyone else come in since I called roll? So that's how we do it. Now, do we go along measuring arc lengths and radius? No, that's really not what we do, but we will figure out how to do this. Now, where theta is measured in radians, this is that ratio. It's equal 1 only when S is equal to 1. Less than 1 if S is less than R, greater than 1 when S is greater than R. Now, let's think. Oh, Terrell came in, snuck in on me. Okay. All right. Anyone else come in, Sister Caldwell? All right. Now, let's think about a circle. Okay. This is the unit circle we're dealing with. What is the distance around the circle called? Circumference, exactly. Does anyone remember the equation or formula for the circumference of the circle? Huh? 2 pi r. Circumference of the circle is 2 pi r. Okay, let's write that down. There it is. Circumference of a circle is 2 pi r. That's just all the way around the circle. Now, if the radius is 1, we have a unit circle, then S would be 2 pi. That's the distance around the unit circle, 2 pi. And the ratio of S to R would be 2 pi to 1. So the radian measure all the way around the circle is 2 pi. And if you get your name, please. Taiwan, got it. All right. Good deal. Anyone else come in, Sister Caldwell? So, all the way around the circle, that angle is, in radians, is 2 pi. What would be halfway around the circle? Second? Pi. Okay. What would be a quarter way around the circle? Pi halves. Half of that would be pi fourths. Now, I bet you know the angles that represent it all the way around the circle. What would that be? How many degrees? All the way around the circle? Huh? 360, halfway around the circle? Half of that, 90. Half of that, 45. This is some before I'm sending you the answer. No, okay. All right. So we already know a relationship between a lot of those angles based on this. Now, if that radius wasn't 1, okay, whatever the radius is, you still have that ratio. So all the way around the circle is 2 pi radians. What's that? A wasp? Okay. Anybody else? All right, good man. I think it was the smell that got it. No, I'm just kidding. Okay. Thanks. So because the circumference of a circle is 2 pi r units, it follows that the central angle of one full revolution is 2 pi r. The ratio of s to r, divide both sides by r, that's always going to be one trip around the circle, no matter what the radius is. S over r is theta, that would be 2 pi. Always. So halfway around would be, and by the way, anyone know what pi is approximately? About 3.14 blah, 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 blah. Well, 2 pi would be 6.28, blah, blah, blah. Okay? So that's how many radius lengths there are in a full circle. About 6.2 pi. 6.28, which is 2 pi. Now, so this would be 6 radians here, 0.25 more, 2.8 here, would get you back to one circle around. So a radian is, so half of that would be 3, this would be 3, but that would be pi radian, 3.14, so this is 0.14 of a radian. And divide this into thirds, and this is a little bit less than 1/6, because this is 180. So 3 radians is a little less than 180 degrees, so 1 radian would be a little less than 60 degrees. It's about 58 something another, but who cares? Okay, that's how we've got this. Okay, there are just over 6 radius lengths in the full circle. No matter what the radius is and how big the circumference is, it's always that. Because the units of measure for S and R are the same, the ratio S over R has no units. It's just a real number. And from now on, they're going to talk about the real number T or the real number theta or something. It's real. We think of it as an angle, but it's just a pure number. No units, but it's in radians, which is a ratio without units, but we usually call them radians, just like they did here, 1 radian, 2 radians. It'd be 1, 2, 3, 4, 5, 6, you know. It's just a ratio. All right. And because the measure of an angle of one full revolution would be 2 pi, then half a revolution would be pi radians, quarter revolution would be pi halves radians, a sixth of a revolution, that would be 1 revolution, this would be 3/6, 1/6 would be over there, that would be pi thirds radians. Okay? So, you know, half a revolution would be pi, so technically, 1 revolution would be pi radians, so a sixth of a revolution would be pi thirds radians. Okay. Oh, I said that wrong. Half a revolution is pi radians, so 1/6 of a revolution and 1/3 of that, which is pi thirds radians. All right, so we already know a lot of equivalences there, and they're pretty straightforward. Here are some of those angles we've already talked about. We talked about pi thirds here. This is half of that, which is pi 6. We're going to find out that is a really favorite angle. Pi fourths, we know what that is. It's exactly half of pi halves. Okay. Pi thirds, we mentioned last week, 1/3 of pi. Okay. This is pi halves, and that's right angle. This is straight angle, pi, and 1 complete revolution is 2 pi. Now we can split these up even finer than that. This is 1 pi 6, 2 pi 6, which is pi thirds, 3 pi 6, which is pi halves, 4 pi 6, which is 2/3 pi, or 2/3 pi. 5 pi 6, 6 pi 6, which is pi, and then you can do 7 pi 6, 8 pi 6, which would be 4/3 pi, 9 pi 6, which would be 3/2 pi. You can split them up and go all the way around. This is 1/4 pi, 2/4 pi is pi halves, 3/4 pi, 4/4 pi, which is pi, 5/4 pi, 6/4 pi, which would be 3/2 pi, 7/4 pi. So you can do every one of them that way. Take them as many times around and as far around as you want to. those are going to be our favorite angles because we know exactly what those angles are. Okay? So get used to them. Get to know them. Okay. Now, a couple more little definitions. I'll let y'all finish that. Like I said, hopefully by Wednesday afternoon I'll have all the PowerPoints out there on Blackboard. All right. Now, I know you're familiar with the Cartesian coordinate system, right? Okay. By the way, how do we get that name, Cartesian coordinate system? Anyone know? Named after René Descartes. He's the guy, French. His names are very similar to this names. Well, René Descartes. He's also a famous philosopher. One of his most famous sayings is, "I think, therefore I am." Pretty incredible guy. He's the one who made the connection between geometry and algebra. It's called analytic geometry, and he did it by using this Cartesian coordinate system. And if you draw your horizontal axis and your vertical axis meeting at the origin, which happens at point 0, 0, that splits the Cartesian plane into 4 quadrants. You all know how they're numbered? Okay, just like this. 1, 2, 3, 4. And again, counting counterclockwise. Remember, counterclockwise is positive and trig. Your angles are positive. So the first quadrant is from 0 to pi halves. Second quadrant from pi halves to pi. Third quadrant from pi to 3 halves pi. And fourth quadrant 3 halves pi to 2 pi, which is back to 0 again. All right. Now, and we number them usually capital Roman numeral. Don't know why, but they usually do that. So we number those quadrants 1, 2, 3, and 4. Back when you were in algebra, you probably focused on when you're doing graphing of things, what was true about everything in the first quadrant. That's important. Positive on the horizontal axis, positive on the vertical axis. How about second quadrant? Negative on the horizontal axis, still positive on the vertical. How about quadrant 3? Negative in horizontal and negative vertical. Quadrant 4? Positive horizontal, negative vertical. Absolutely, y'all got that down. We're not going to use that yet, but we will be using it later. Okay, that's what I wanted to remind you. Okay, notice that the angles, if you're in the first quadrant, here's another thing. All these angles are between 0 and pi halves. What do we call those? Acute angles. Okay, yeah. Acute angles. Okay, never mind. These are called acute angles. If you're in the second quadrant, they're no longer acute, but they're obtuse. Exactly. Something between pi halves and pi, those are called obtuse angles. We don't have special names for them down here. Those are first and second. Now, there is one other that they don't say, but occasionally will reference. When they say a quadrantal angle, that means one that falls on the quadrant. That one, this one, you know, those that fall on the quadrants. You know, in other words, on the axes. Those are called the quadrantal angles. So they're not covered in either one of the quadrants. So this is less than less than less than less than. When they're on it, then there's the quadrantal angles. So don't sweat that, but if you had wondered about that, those are all less than, what about if they're equal to? I'm sure you were wondering about that. Okay. Now, two angles, I think we used this term before, didn't we? Coterminal. What did that mean? We always count all angles having the same initial side. The final side is called the terminal side. If they're coterminals, they have the same terminal side as well. So two angles are coterminal when they have the same initial and terminal side. For instance, the angle 0 and 2 pi, I just made reference to that before. Wrong way. Okay. This was 0 here. 0 to pi has to pi to 3 has pi, and 3 has pi to 2 pi. So I said that's the same as 0. So these two, theta equals 0 and theta equals 2 pi, are coterminal angles. They're the same angle, okay? It's just that one is they both have the same initial side, which is a positive x-axis, same terminal side, which is a positive x-axis. That's true for theta equals 0 and theta equals 2 pi. So those are coterminal angles. They have the same initial and terminal sides, okay? But not just those, any two angles. Pi 6, remember that's one just above horizontal. But if you go all the way around again, you'll have 12/6 pi plus one more is 13/6 pi. That's coterminal with pi 6. Or, if you went pi 6 here, and then went negative 11/6 pi, that's coterminal. Same initial and terminal side. This one in the negative direction. Okay, you can find an angle that is coterminal to any given angle theta by just adding or subtracting 2 pi to it. Okay, because that's all you're doing. If this is the angle of interest, theta, then go 2 pi, one complete revolution, you're back at the same place. Or go 2 pi in the opposite direction, you're back at the same place. So you're adding or subtracting 2 pi, or 4 pi, or 6 pi, or 8 pi, any multiple of 2 pi to the original angle. So a given angle theta has infinitely many coterminal angles. You can go around as many times as you want to, in either direction that you want to, okay? So how we express that, theta equal pi 6, that's the given angle, is coterminal with every angle that is pi 6 plus any multiple of 2 pi. So we call that 2n pi, where n is any integer. Positive, negative, 0, it doesn't matter. Those would be coterminal angles. Does that make sense? All that means is whatever your angle is, go around so many. Every time you go around 2 pi, that's up another n, or down another n if you're going in the opposite direction. So anytime n is any integer. Does that make sense? Later we'll be doing, when we're solving equations, so find all the angles theta that make this true. If they really mean all, then you have to include all the coterminal angles. And we'll be using 2n pi a lot. Okay, so here's example 1. For the positive angle 13/6 pi, oh, they tell you everything to do. I just really don't like the way they do this one. Given the angle 13/6 pi, it says find the coterminal angle with it. Okay? How would you do it? They've already told you. Subtract 2 pi. Well, how many 6 is 2? How many 6 is 2? 6. Second? A little louder.
1/6. You said 1/6.
Okay, how many 6 is 2? The number 2, how many 6 is that? 12/6, exactly. So if you're going to subtract 2 pi, that's the same as subtracting 12/6 pi, right? From 13/6 pi, and what do you get? 1/6 pi, exactly.
Okay, I said.
Okay? Now, if you wanted to add 2 pi to it, that would be 12/6 pi plus 13/6 pi would be 25/6 pi. Exactly. So you can add or subtract any multiple of 2 pi to 13/6 pi, and you get a coterminal angle. Now here's how we do it graphically. Here is 13/6 pi. You start here. You go to 1, 6, 2, 6, 3, 6, 4, 6, 5, 6, 6, 6, 7, 6, 8, 8, 12, 6, 13, 6, and then subtract from that one complete revolution, which is 12, 6, and you wind up 12, 6 pi, and you wind up with 1, 6 pi.
How would we know to add or subtract?
If it's asking for, okay, if they ask for an acute angle, then you got to make that smaller, so you would subtract. If it's asking for a larger angle, you have to add. If they're asking for a positive angle, say if they gave you this and say give me the next closest positive coterminal angle, you have to add 2 pi to it. If they say the closest negative angle, subtract 2 pi from it. So you just go by the problem. If they don't specify, you can add or subtract. Okay, but always 2 pi. Always 2 pi. Okay? Now the B part. I want to do this. For the negative angle, negative 2/3 pi. Let me get my pen activated. Okay, negative 2 pi over 3. Okay? For that angle, find a positive coterminal angle. How would you do that? Second? Okay, you're going to add 2 pi to it. But we love our fractions, but
Yeah, we get 6 pi over 3.
yeah, let's make that 6 pi over 2. That's just, or 3, I'm sorry. 6 pi over 3, that's 2, right? 2 pi. And that would be what? 4 pi thirds. Okay, let's see how they did. Okay? So we go for the negative angle, negative 2/3, add 2 pi to it to obtain the coterminal angle, and they get 4/3 pi. Good for this. Okay? Okay, let's show you how they got this. Here's negative 1/3 pi would be down here. Remember, this is pi. Okay, that would be negative pi. 1/3, 2/3. So that would be negative 2/3 pi is here. Add 2 pi to that, and you wind up with 4/3 pi. 1/3 pi, 2/3 pi, 3/3 pi, 4/3 pi. Yeah. Get used to thinking in terms of pies. Because now, I think we said this in the last class, let me say it again. I'll say it repeatedly. Most of the time in calculus, and hopefully at least some of you are going on to calculus, is that right? All of you? Fantastic, okay? If you're going on to calculus, when you're dealing with angles there, trigs, and stuff like that, just about everything is going to be in terms of radians, not degrees, okay? Just about always. I don't want to say always because you'll always find some exception. Almost always, okay. All right, so let's continue here. Here's a couple of other definitions. Two positive angles, alpha and beta, positive angles, alpha and beta, are complementary. Okay? No, this is C-O-M-E-L-E, not I. Okay? Now, what does that almost look like? What would you almost see there? Complete. Okay? They're complementary angles because they complete each other, or they complements of each other when the sum is pi halves. What do we call pi halves? What angle do we call that? A right angle. And, you know, the old Greeks, they called it right angle because they considered it a perfect angle. The greatest strength comes from a right angle, okay? That's why most buildings are built that way, okay? So they're complementing if they complete each other and make a sum of pi halves, okay? Now, guess what? If they're going to add to 90 degrees, pi halves, then, and they got to both be positive, both of these are what kind of angles? Acute angles, exactly. They're acute angles because they can't possibly add to pi halves unless they're between 0 and pi halves. And that's what makes them acute angles. Now, two positive angles are supplementary, okay, or supplements of each other when their sum is pi, if they add to be pi, okay? One supplements the other. Now, guess what? They're both positive now. What are the three possibilities? Either one is acute and the other obtuse, okay, or they're both not. Pi halves, okay? The only possibility. One's acute, the other obtuse, or one's obtuse, the other acute, or they both happen to be right angles, okay? So, two complementary angles, both of them must be acute angles. Add to pi halves. They're positive angles. Okay? Two that add to be pi, either one's going to be acute, the other obtuse, one's obtuse, the other acute, or they're both right angles. Only way it can happen. Make sense? So those are those two definitions. Complementary and supplementary angles. Okay? They skipped example 2. So let's go back. Oh, goodness gracious. Let's do it here. Example 2. What is the complement of 2/5 pi? What is the complementary angle to 2/5 pi? What's true about the complement of this angle? Say again? Pi thirds? Okay. Let's name it something. Pick a name for it. An unknown. Anyway. Say again? George. Okay. I'll just put G, okay? All right. Capital G for George. 2/5 pi plus George has to equal what? For them to be complementary angles, what would it have to be equal? Yuck. Pi halves, exactly. Okay, now to do that mathematics here, we need to do common denominator, because these are fractional forms. What's common denominator between 5 and 2? 10, okay? So this will be how many tenths of a pi? 4/10 pi plus George is equal to 5/10 pi. Ooh, 5/10 pi. That's ugly. Okay, I can't write. Okay. So guess what George has to be? 1/10 pi. So George has to be pi tenths. Okay. Make sense? All right. What would be the supplement of 2/5 pi? Say again? No, they have to add to be pi. So give me a name. Oh. Say again? Fred. Okay, well, it'll be Fred then. And that's going to be what? Some of these are going to be what? Someone said it? Pi. Okay, I love pi. Okay. Now, again, we need least common denominator. What would that be? 5. How many fifths is 1? 5/5. Okay. So anyone know what Fred is going to be? 3/5 pi. Buy that? Okay. Now, how about 4/5 pi? What is the complement of 4/5 pi? Okay, the sum of that, okay, you want to name that one? Randy, okay, is equal to, what do you say it have to be? Pi over 2, okay? Again, you got to get common denominator. What would it be? In this case, it would be 10. So what would that be? 8/10 pi plus Randy would be how many tenths? 5/10 pi. What would Randy have to be? A what? Negative 3/10 pi? Is that what you said? Anything wrong with that picture? Complementary angles always are positive. Can't happen. Why couldn't that happen? Because what else are complementary angles always? Acute. And what is 4/5 pi? Obtuse. You can't do it. This does not have a complement. 4/5 pi does not have a complement because it's an obtuse angle. It's greater than pi halves. So you can't add another positive angle to it and get pi halves. Does it have a supplement? Does 4/5 pi have a supplement? What? 1/5 pi. Its supplement would be pi fifths. Because when you add them together, you get pi, right? So 4/5 pi doesn't have a complement, but it does have a supplement. Make sense? All right. And by the way, I take it most of you have used this text before. Is that right? You did Math 112? Any of you? Okay, you did. You came into 113. Let me tell you a little something about this text. Every example I think in here is followed up by a checkpoint, which is a very similar type problem. I highly recommend one of the best ways to keep up with the material is as soon as you get out of class, as you don't have another class, whenever you can, sit down and do the checkpoints for all the ones we did in class, okay? That way you'll do it while it's fresh on your mind and reinforce that. What if you've already forgotten? Maybe you have 3 classes in a row or something like that. And by the time you get there, you're brain dead and say, man, I can't remember how we did that. Well, guess what? Every one of these checkpoints, if you'll notice here in the print here, it says audio video solutions to these checkpoints in English and Spanish is found at larsonprecalculus.com. This book has the best online supplements or auxiliary material of any book I've ever taught from. The author's good. Pre-calculus is pre-calculus. It'll be sort of hard to screw that up, but he gives the most supplementary material of any author I've ever seen. Free. Anyone can go to it. You don't have to buy a website to get it. It's free. Okay? Hang on to that because a little bit, when I give you homework exercise, I'll point something else out. All right, so let's continue. Now let's do degree measure. Any questions on complements and supplements? Understand what's going on there? Okay. Now, degree measure. Now, I told you about the Sumerians before, didn't I? No? Yeah, okay. They had some sort of base 10 and 6, some sort of numbers, and so they used everything in the 60s, okay? And 60 degrees, 60 minutes, and now 60 seconds. Yeah, we get a lot from the Sumerians, the ancient Babylonians. So I think that's where we got these degrees. The second way to measure angle is in degrees, denoted by the symbol, a superscript degree symbol there, okay, a little circle up there. A measure of 1 degree is equivalent to the rotation of 1/360th of the way around the circle. That's not very much, okay? That's of a complete revolution around the vertex. 1/360th of half, that would be pretty small. That would be 1 degree. So to measure angles, it's convenient to mark the degrees on the circumference of a circle, and here's how we do that. Work all the way around the circle. You've already answered it to me today. What is it? 360 degrees. So halfway around would be, and half of that would be, and half of that would be, a third of 90 would be 30, 2/3 would be 60. This would also be 3/3 would be 180. I'm not sorry. Twice 30 is 60. 3 times 30 is 190. 4 times 30 is 120. Twice 45 is 90. 3 times 45 is 135. And then you have another 30 degrees added to 120 would be 150, and then you get 180. 210. 5/4 would be 225. 4/3 would be 240. 3/2 is 270. So you get, these are our favorite angles. We'll get to love them. Okay. So get used to it. Now, if you think back, what was one complete circle in radians? 2 pi. Half a circle, pi. Half of that, pi halves. So pi halves is 90. Pi fourths is 45. Pi 6 is 30. Pi thirds is 60. You'll get to think of these in very simple terms all the time. So this is how to think of them in terms of degrees. Then superimpose on that what we already talked about in radians, and you've got a lot of comparisons there. Now, 1 radian was almost 60, but not quite. It's 58 something or other. It's an irrational number. And here's the chart. All right. So we're still missing Kenesha. Juwan Taylor, we haven't seen from the beginning, right? And that's all. Good deal. Good attending class. Way to go, folks. So, the full revolution, counterclockwise. Remember, we always go counterclockwise. Corresponds to 360 degrees. Half a revolution, 180. Quarter is 90, and so on. And, just like I said, 2 pi radians is 1 complete circle. That's equivalent to 360 degrees. Or 180 degrees is pi radians, which gives us a way to go back and forth between radians and degrees. This ratio here, 180 degrees is pi radians. Okay? Now that's done as an equal sign, but what we do is write it as a ratio. So give me an angle, any angle you want to. Name a number. Say again. 45 degrees. Is that what you want? Okay. So, oh, goodness, why do I keep doing that? Okay. Wrong direction. Okay. So let's say we have 45 degrees. Now we're wanting to convert that to radians. Now remember, radian really is a unit, but I'm going to treat it as if it's one. Okay? Now if I'm doing that, now this is how I do all my conversions in physics and math and anything. If I'm doing a conversion, I write down what we're given with the unit, and then I write 2 blanks. The first blank is for numbers. The second blank is for units. And then equal to, this blank is for numbers. I know what unit I want. You started in degrees, I want this in radians. So here's how I do all my conversions. I put the units in their place. Determine where each unit goes. If you got degrees going to something to get radians, what is going to happen? On top and on bottom, one's got to be degrees, one's radians, what goes where? Always put the units in. Second? Radians on top, absolutely. Okay? And degrees on the bottom. Why? So degrees will cancel out and you wind up in radians. Right? Does that make sense? Now you match the numbers with the unit. And this is all you have to remember. 180 degrees is pi radians. So, radians is pi radians, 180 degrees. And there you have it. So, what does this yield? This yields 45 over 180 pi. And that will be how many radians you have. Okay, because the degrees canceled out. Well, I know that 5 will go into 45 how many times? Well, actually, 9 will go in 45 5 times. 9 will go into 180 how many times? 20. And 5 will go into 5 once. 5 will go into 24 times. So this is pi fourths radian. We knew that, didn't we? That 45 degrees was pi fourths radians. That's how you can do any of these conversions. That one we knew already. Now what the book likes to do is, if it's going one way, you multiply by pi over 180, and or the other way you do 180 over pi. Well, if you just put the units in their place and then match the numbers with the units, you don't have to worry about whether you multiply or divide by this or that. All you have to do is match the units and numbers. Okay, get the units in their place and match the numbers. So they say leads to the conversion rules. I've already given you my conversion rule. Here's what they say. To convert degrees to radians, multiply by pi radians over 180 degrees. Well, yeah, that's true. But if you do it the way I said, you don't even have to memorize anything. All you have to do is put units in their place, match the numbers with the units, and you're guaranteed to have it right. As long as you do it right. If you convert radians to degrees, you don't have two different things. Do the one thing and put units in their place and match the numbers with the units. It'll come out being that every time. Okay? So, here's those favorite angles again. Pi 6 radians is 30 degrees. Pi fourth radians is 45 degrees. Pi third radians is 60 degrees. Pi half radians is 90 degrees. Pi radians is 180. That's the one we based on. And 2 pi radians is 360 degrees. And then you can do all the other intermediate ones of these. This would be one over here is 2/3 pi radians would be 120 degrees. 3/4 pi radians, that's 1/4, 2/4, 3/4 pi radians would be 135 degrees. Okay? And every one that you want to do here. This one would be 5/6 pi radians would be 180 minus 30 would be 150 degrees. So you can match all up all the way around the circle. Okay? Make sense? Pretty straightforward. Use it. Now, I have done this before. I don't have a copy of it anymore, but all of you can find it because the internet's out there. You can get the unit circles with all these things listed on. You know, if that helps you, get one. Have it with you so you can look it up and use it anytime you want to. All right. Now, here is a very important thing. When no units are specified, guess what we're dealing with? Radian. Because radian is really a dimensionless quantity. It really isn't a unit. We use it as if it is, but it really isn't. So in other words, if you see theta equals 2, don't assume that's 2 degrees. If it doesn't have a degree symbol, that means 2 radians. Period. Now, if it has a degree symbol, that means 2 degrees. But anytime there is no unit given, you assume that means radians. Always. Okay. Now, I hate that they're showing you everything. So let's go back and do this. Example 3. What if they gave you 135 degrees and said, how many radians is that? Convert those degrees to radian. What do you do first? Put the units in their place. What unit goes where? Degrees on the bottom, that puts radians on top. Okay? And how many radians equals how many degrees? Pi radians is 180 degrees. Okay? Degrees are going to cancel out. That leaves your radians. 135 and 80. Anyone recognize anything or go into both of those? Second? 15? Is that what you said? It might. Let's see if it does. 15 will go to 135 how many times? I don't think it. Yeah, it will. Huh? 9 times? Okay. 15 will go into 180 how many times? 12 times. Okay. Any further? That'll be 3/4. So that is 3/4. 3 pi. 3/4 pi. Don't forget your pi here. Actually, I probably should have that 3 pi over 4, but doesn't matter. Okay, it means the same. All right. What if we had 540 degrees? Okay. And we're trying to convert that to radians. Same deal. Put the units in their place. Radians on top, degrees on the bottom. Same ratio. Pi radians is the same as 180 degrees. Degrees cancel out. Now I know I can divide out a 0. And what will go into 54 and 18? Second? 180? Yeah. Yeah, I already got rid of the 0. So, okay. I know. What did you say? 18? Okay. 18 will go into 54 how many times? Second? 3 times. 18 will go into 18 1 time. So this will be 3 pi radians. Okay? Indeed, is that true? Well, let's think about it. Let's think about 3 pi radians. 3 pi radians will be 1 pi, 2 pi, 3 pi. Okay? Well, let's do it in degrees. 180 degrees, 360 degrees, and 180 and 360, sure enough, is 540. Okay? So, yeah, that's right. All right. They have a checkpoint here. Let's go it the other way. What if you had negative pi halves? I can't write. Let me clean that up a little bit. My eraser won't come in. Okay. All right. And we're trying to get this to degrees. So what unit goes where? This is radians. What unit goes where? Help me, help me. Always put the units in their place. Degrees on top, radians on the bottom. Very good. And what numbers match those? 180 degrees is the same as pi radians. Okay? Hey, I can cancel out pi there. And I can cancel 2 into 180 how many times? 90. So this will be minus 90 degrees. We knew that, didn't we? That minus pi halves is minus 90 degrees. Absolutely. Oops, I put degrees there twice. I didn't need but once. Oh, it didn't take. My eraser's not doing right. Okay, good deal. All right, let's do the last one. What if we had 2 radians? Okay. What do I multiply by what? Or to get degrees. What unit do I put where? Okay, degrees on top, radians on the bottom. 180 degrees is how many radians? Pi radians. And guess what, folks? Not much we can do here. The radians are going to cancel out. We know that. And this will be 360 over pi. That's your answer, okay? Now, if you have a calculator, do 360 divided by pi, you'll get so many digits, but I would round it to the nearest whole digit. They do 114.59 degrees. Now, I have a little bit of an issue with that. They say this is they don't even say, yeah, they do approximately equal to 114.59 degrees. And the book, and I go around and around on this one. It's not just now, but in lots of places. The physicist in me says this is only one significant digit. So how can you get 5 significant degrees? You can't. Now, if they said 2.0000 radians, that means you have 2 radians to the nearest 10,000th of a radian. So yes, you could say that many. But basically, technically, you always say that's approximately 100 degrees. Now, that's a gross approximation. I would say 115 degrees, just to have a whole number. So, why 0.59? It's an approximation anyway. You can't get that many significant digits out of one. So, yeah. But I won't count off for it. But I just don't think it's a good practice. And again, that example has a checkpoint, so pay attention to it. All right. So here's our 135 degrees. I'm sorry, we should have gone back and done this. That's exactly what we did, but I didn't memorize the formula. Multiply by pi radians are 180 degrees. Set up the units so they have to cancel out, and then match the numbers with the units. Okay? That gives you 3/4 pi radians, which is exactly what we got. 540 degrees was and why they changed from degrees to DEGs, I mean, there's no reason for it. The degree symbol is just as good, but they did it that way. That's fine. And then they did it up there. I didn't notice it. So that comes out 3 pi radians, just like we did. And then they skipped the next example, but we've already done that. All right, so here's an application. The radian measurement formula says that theta is equal to S over R, right? That's what we can do. Multiply both sides of this equation by R. Now S is equal to R theta. That is what we call the arc length formula. S is equal to R theta. For a circle of radius R with a central angle of theta, the arc length of that S is given by S equal R theta. Always. Always. However, what is theta measured in? Radians. This formula does not work with degrees. You have to have your angle in radians. If R is equal to 1, then S is equal to theta. Okay? And the radian measure of theta equals to the arc length. If your radius is 1, which is going to be what we call a unit circle. So that's why they're mentioning that now. Okay? Let's do example 5. A circle of radius has a radius of 4 inches. Okay? So when you're doing this, I would also put units in here. Okay, 4 inches. Find the length of the arc intercepted by the central angle of 240 degrees. There's your central angle of 240 degrees. What we're looking for, what is the value for S? This is what we're looking for. How do we do that? Say again? Okay, and what is that formula? S is equal to R theta. Is that what you said? Okay, and then what do we do from here? 4 inches times 240 degrees. Agreed? Why not?
I said, yeah.
Yeah, okay, fine. Okay. Thought you were contradicting her, okay? Does anyone disagree? What's wrong with that picture? Okay, this number one is going to have you an arc length of something on the order of 960 inches, which would be 80 feet. So a 4-inch radius circle is going to have an arc of 80 feet. Yes. It's not in radians. You cannot do this in degrees. What do you have to do first? Convert the 240 degrees. So let's do that. 240 degrees. Multiply it by blank blank equal blank radians. It's not really a unit. What unit do we put where? Radians on top, degrees on the bottom. What unit numbers do we match with these? How many radians make how many degrees? Pi radians make 180 degrees. Okay, now your degrees are going to cancel out. The zeros will cancel out. And then what will go into 24 and 18? 6. 6 will go into 24. 4 times. 6 will go into 18. 3 times. This will be 4 pi thirds radian. 4 thirds pi radian. That's what we put in here. Okay? Not 240 degrees, but 4 thirds pi. Okay, and what does that give us? 16 pi thirds. Now, folks, to get a good quick estimate, what's pi? 3.14. So that's a little bit greater than 3. They almost cancel out. Your answer will be something a little bit greater than 16 inches. That makes more sense, okay? A little bit greater than 16 inches. If you plug that in your calculator, how many inches do you actually get? (16 pi divided by 3). Anyone got a calculator? Second? Anyone get it?
I have 16.
Second?
16.
Okay. They did 16.76. I actually like your answer better because, but still it's not good enough. I'd say approximately 17 inches. Because how can you get 4-digit precision out of 1-digit input? You can't really. This is math, it's not physics, so they don't pay attention to that. But I can't even swear that, I mean, really you should say about 20 inches. But actually, this is a lot closer. I'd say 17. That's close enough for government work. Yeah, you can print out, write all the digits your calculator gives you, but look, they're meaningless. So 16.8 would be fine. 17, I think, would be a little bit better, more precise. I mean, more in tune with what the problem is. Now, if they give 4.0 inches, then 17 would be correct. Yes, what you say? A lot of people do that. They did it to 4 significant digits. Okay, maybe they're rounding to the 2 decimal places, but I think that's a little ridiculous when you don't have enough precision to do it. So I don't count off, but if you're going to, ask it how many of you are going into calculus, how many of you are going to take physics ultimately? Quite a few of you there too. Get used to significant digits. So why practice something that's not good? Okay, so, all right. They have a checkpoint. I would definitely, when you have a chance, do those checkpoints. Okay. So here's what they did. They went by their formula, multiplied, first convert it to that and do that. But we did the same thing. We just matched up units and made them do. Got exactly the same result. That is 4/3 pi radians. Multiply that by, put that in the formula. R is 4 inches. Theta is 4/3 pi. That is 16/3 pi, which is something a little bit greater than 16 inches. I would round that to 17 inches. Okay. Note that the units for R determines the units for R theta, because the theta is a dimensionless quantity, has no units. We call it radians, but it has no units. So whatever your units for the radius is, that's going to be the unit for the R. That's what they're saying. In physics, you pay a lot more attention to the units than they do in math. All right, so here's another application. The formula for the length of a circular arc can help you analyze the motion of a particle moving at constant speed. Now, that's the key here, along a circular path. So we have actually two types of speed. Linear speed, which is usually measured in linear units, miles per hour, feet per second, meters per second, kilometers per hour, centimeters per second, whatever it is, some linear distance divided by time. Or angular speeds, which is so many radians per second. You could have degrees per second, but usually we don't. We use radians per second. That's an angular speed. Consider a particle moving at a constant speed along the circular arc of radius r. If S is the length, sorry, my head's clogging up on it, I don't know why. If S is the length of the arc traveled in time t, then the linear speed, v, would be S over t. This is traveled over time to arc length over time. Moreover, if theta is the angle in radian measurement corresponding to the arc length S, the angular speed, now that may look to you like a little strange looking little W. It's not. Does anyone know what that is? Lowercase Greek omega. Capital omega is like this. Okay? Little omega looks like that. Very different looking. This is omega. The angular speed is in omega. The particle is given by the angular speed is the rate at which the central angle is changing, theta over t. So that would be radians per second. Would be the units for angular speed. Linear speed, centimeters per second, meters per second, feet per second, whatever you're dealing with, the angular speed is radians per second. All right. Now, here's another sort of definition here. This is a big step. Let's go back. They skipped examples 6 and 7. That's what got me a little confused here. So let's go back and see if we can find a place. Okay, this is about the best place to do examples 6 and 7. All right. Most of you don't have your books, right? That means I got to draw this. Thank you very much. All right. The second hand of a clock is 10.2 centimeters long. So I'm going to draw me a clock face. I don't draw circles very well. Okay? And this will be 12. This will be 3. This will be 6. This will be 9. This will be 1 and 2, 4 and 5, 7 and 8, 10 and 11. Okay, there's approximately your clock face. Okay, there's the center of it. The second hand, wherever it is here, this is the second hand, that is 10.2 centimeters long. It says find the linear speed of the tip of that second hand as it passes around the top. So linear speed, how fast is that going? So this is what we're looking for, velocity, which is linear speed. All right. Linear speed is length per time, right? Now, and this is the second hand, remember that? How far does the tip of this thing go if it makes one complete revolution? Say again?
360 degrees.
Okay, 360 degrees. Okay, here he is thinking in degrees. 2 pi. Okay, let's think in terms of radian. Is 2 pi radians is the angle distance it makes times the radius. That's going to be your arc length, right? S equal r theta. Theta being in radians. So it's r is 10.2. So the distance traveled is equal to r theta, which is 10.2 centimeters times 2 pi theta. So this is 20.4 pi centimeters. That's the distance it travels. Now, how long does it take the second hand to make one complete turn? Wait a minute, what? Time. How long does it take a second hand to make one complete turn? Someone may have said it. 60 seconds. That's what a second hand does. It goes around the clock once every minute. 60 seconds, right? So the distance is that. The time is 60 seconds. So the speed, V, is equal to 20.4 pi centimeters over 60 seconds. Okay? My writing sort of stinks here. Let me see if I can clean that up a little bit. I slashed my zeros, by the way. Sorry about that, but old habit from the Navy. Okay. All right. So if you got a calculator, plug it in. 20.4 times pi divided by 60. I can give you approximately what that's going to be. Well, I'll let you do it. .07. Okay, I heard a 1.07 centimeters per second. Centimeters per second. Okay, just a little over 1 centimeter per second. Okay, they do 1.068. Oh, how sad. We've run out of time. Okay, get over it. All right. We'll start next time on example 7. We almost finished the section. So let me give you homework here. Do either 7 or 9 or both. Do 11. Do 13. Do 15. Do either 17 or 19. Either 21 or 23 or both. Do 25. Do 27. Do 29. Do either 31 or 33 or both. Do 35. 37. Either 39 or 41 or both. Either 43 or 45 or both. Do 47. Now 47 is a type of problem we haven't done before. Try to work on that yourself. If you can't figure it out, ask in class and we'll go over that. Why they threw one in here, they didn't do it. Okay? 49, same way. If you can't figure it out, bring it to class and we'll work on it. Do 51 and do 53. Do 55. Okay. We didn't quite make it to a sector, so stop at 55.
Someone
No.
and I have got the last couple of homework.
Okay. All right. I'll go over them again. You can hear them on YouTube video too. Yeah. Yeah, take a picture. 9 or 7 or both. This right here. 9 or 7 or both. 11, 13, 15, either 17 or 19 or both. 21 or 23 or both. 25, 27, 29, either 31 or 33 or both. Okay, you need a picture of that? Okay. But on the next page, okay, and you want to take pictures, you might want the next page too. 35, 37, either 39 or 41, either 43 or 45, 47, 49, 51, 53, and 55. Stop at 55.
This is due Thursday.
Okay. The homework is for your own cultural enlightenment, okay? These are what your test questions are going to look like. Do these, you'll be ready for the test.
Oh, so they're not like
You don't have to turn them in. If you have problems with them, you can turn them in and I can help figure out why you're having problems.
yeah, you got AirDrop?
I never used it. So you can take
Good deal, thank you. I got a paper topic, good deal.
Oh,
I turn it on to everyone.
yes.
Oh, I got a paper, really good deal. First paper of the term. Way to go, class. You win the prize.
I'll get back to you on that.
All righty.
I took like a whole bunch of pictures, so I'm just gonna like
Okay.
them all.
All righty. Good deal.